Welcome to this lecture on data structures. Today we're going to talk about one interesting topic of applications of stack abstract data type in computer science. As we had already studied, stack is a LIFO abstract data type which has a collection of elements with the operations called as push and pop. Push would put elements into the stack and pop would remove elements out of the stack. And one property of pop is that it would remove element out of the collection which is the most recently inserted. So we defined the abstract data type of stack and also saw implementations of stack using linked list, using arrays, using the list abstract data type, contract, and so on and so forth in our previous lectures. In today's lecture, let's go ahead and see what are different applications of stack in the area of computer science. So one of the foremost applications of stack in computer science is during the process of function calling. So if there is a function f which has a bit of code in it, and then it in turn calls another function g, and after the return of the function g, it uses a value returned by g to compute some value and return some other value as the written value of the function. What happens just before g is called is that there is a stack that is maintained which is called as a call stack. And all the local variables of the function f at the point that the call to g is being made are bundled into what is known as an activation record. And this activation record is pushed onto the stack so that when the call to g is returned with a return value which is then assigned to I, f has access to the state of the function just before g is called. And that activation record is then popped out and then used in the further computation to compute the return value of f. So the stack is used as a temporary storage for f to bundle up its state into an activation record just before it calls another function, and then use the stack to store that activation record, and then pop out the same activation record after the function call it has made has returned to reuse that activation record and pull out the values that were existing before the function call is made to compute further data. So this stack has activation record of f which is pushed just before call to g is made, and after the call to g returns to f, this same activation record is popped out and used in the function. So if you represent this as a generic call graph, so let's take a function f which calls a function g, which in turn calls a function h, which might in turn call h itself. So this is where you have recursion, where a function calls its own self with potentially different parameter values, and then this goes on, and then say you have another call to h, and then this h returns back to the previous call of h, this again returns to the previous call of h, and then this returns to g, and then this returns to f. So this function call stack is maintained in this function call graph is maintained in a stack. So when f calls g, f's activation record, let's call it AR of f, is put into the stack just before call to g is made, and g basically calls h. So just before h is called, activation record of g is put into the stack, and activation record of h is put into the stack when just before it calls its own self. So this is the first instance of h calling its own self, so I'll call it activation record of h, the first instance. And then when the second instance of h calls the third instance of h, the activation record of the second instance of h is stored in the stack. When the call that's made to this last h returns, what happens is that this, so let's name this the first instance of h, this is the second instance of h, and this is the third instance of h being called. So this method would pop out the top element of the stack at that point and then use it to proceed forward with its computation. So this is the state at which the method was when the call to the third instance of h was made. So at this point, when h of 3, the third instance of h is returned, the second instance of h pops out the whatever is there on the top of the stack and uses that for the computation. And when this second instance of h returns to the first instance of h, the first instance of h then pops out the top element of the stack as present at that instance, and then uses that activation record to pull out the local data as it was before the second instance of H was called, and then uses that for computation. And when first instance of H returns to G would pull out its own activation record and then uses that for the computation. And at the end, after the full unwinding of the function calls, F would ultimately pull out its own activation record and use it for further computation. So it is ensured that because of the property of LIFO, the last in first out property, it is ensured that whenever the function calls the pop on the stack, it ensures that the LIFO property ensures that its own activation record is available at the top of the stack. So the general heuristic that a function call follows is that before it makes a call to another function, it creates an activation record, pushes that activation record to the stack, and then makes the actual function call. And when this function call returns, it pulls back the top of the stack, which is it pops out the top value of the stack and uses that. So it gets back the created activation record and then uses that for further computation. So any change in the stack that is done within the function call would be expected to be undone with a series of pops when the calling function calls the pop after the function call is done. So this is one of the applications of stack. Recursion is seamlessly supported by this mechanism. When people see the error of stack overflow, this generally happens when you have recursive code and the call stack is so deep that the call stack that is used by the system runs out of space. So there is a limited space for the stack available for programs, and when this call stack runs out, when you have a deep enough call that calls its own self and so on, and this exceeds the limit of the number of activation records that can be put in the stack, you encounter the stack overflow error. And this is basically the application of stack, which supports function calls, including recursion. Moving on, stacks can also be used to parse or validate languages which are called context-free. So, for instance, as an example, take the sentence which has parentheses, and you want to design a parser that would validate whether expression using the parentheses is well formed or not. So your parentheses are balanced. You want to write a program to check if your parentheses are in a well formed way. So this also uses a stack, and the way stack is used in this case is pretty simple. So you have whenever you encounter a left parenthesis, you push it onto the stack. So you encounter left parenthesis, I pushed on the stack. Second left parenthesis, again I push onto the stack. And whenever you encounter right parenthesis, you pop out the one left parenthesis. And then for the next right parenthesis, I pop out the next left parenthesis. Left parenthesis, push, left parenthesis, push, right parenthesis, pop, right parenthesis, pop. And at the end of this whole string or sentence, if your stack is empty, that means that your parenthesis is well formed. It's a very simple application of LIFO to validate context-free languages. So this is a very simple sentence I have from a context-free language. There can be more complicated sentences in context-free languages that you can use a stack to validate or parse. Moving on. Another application of stack is in solving problems that involve backtracking to get to the solution of the problem. So for instance, if you have a problem that has many possible next steps to take, you basically take one step, and then if you want to do a depth first exploration of solutions, you would have to put all of these unexplored paths into the stack. So if you enumerate them as 1, 2, 3, these 1, 2, 3 are put onto the stack. And say for instance, you have 0, 4, 5, 6, and you want to say this is 7. So you're at the path where the decision 5 has been taken, and you checked for 6 as well, but then 6 didn't work out. And before you go to 6, you put 7 onto the stack because this is still unexplored. And when you explore 6 and you did not find a solution, you get back to 5, then you would want to check if there are other paths that originate at 7. So you basically pop out the stack at that instance and check if it has any further paths down that node, and then you evaluate these alternatives as well. And if you don't find anything in 7, you would go back to the next element in the stack, which is what was saved when you were going down the path from 4, which is basically the 3, and then that would be then explored. So So this is an application where you would use a stack to keep track of states that are yet unexplored, and you're doing a depth-first exploration of the solution space for problems. One most famous application of stack is what is known as infix to postfix conversion of expressions, which we'll be talking about in more detail in the future lecture. But if you have an arithmetic expression on the form a plus b star c, for example, which is kind of an infix format where the operator is present in between the operands, this is more a human readable or human digestible format. This has to be converted into a machine readable format, which is known as a postfix format, which has operators at the end of the operands instead of having them in the middle of the operands. And so this is a plus, so you have operators at the end of the operands rather than in the middle of the operands, and then you have C then start. So this is more of an expression that a machine is comfortable processing in a single traversal. So this is also where stack is used to convert from the infix format to the postfix format. And once the postfix format is computed, so you have an expression of the form 1, 2 plus 3 star, which is kind of a postfix format. To evaluate this postfix expression and to get to the result of the expression, we also use stacks. So the result of this expression is 1 plus 2 is 3, and then 3 star, which is 9. So this conversion of this postfix expression to the value of the postfix expression is also done using stacks. So these are the high-level applications of stack in computer science. To summarize, we have function calling, including recursion, and then we have parsing of context-free languages, and we have backtracking solutions, and at the end we also have the infix to postfix conversion and postfix evaluation. In the next lecture, we'll be talking about the infix to postfix conversion and postfix evaluation in more detail and understand how this works and how we can effectively use stacks to arrive at the solutions for these two problems.